So my name is Gabriel Chapman. I'm a Senior Solutions Architect here at Fungible. I'm going to walk you through some of the performance testing that we've done, kind of walk through the Fungible Storage Cluster, Storage Initiator, some of the functions that we can do and perform in kind of real-time type of aspect, and then kind of our container solution integration and how we integrate with the great world of bare metal composability containers. So it's kind of our agenda here. Like I said, I will probably jump around a little bit to make sure that we understand what we're doing. But to point out what we have here is a traditional fungible storage cluster where we would have storage that clients can connect to from the host side, either with a Fungible Accelerator card or with the native driver that sits within the side, a Linux kernel, so like a modern Linux kernel that can leverage it. For purposes of our demo, what we have here is essentially a 3-node fungible storage cluster, a composer, which is our out-of-band management, or it's the control plane. We have a 100 gig top of rack switch. We have a management network, and then we have 12 physical servers with Linux running on them that are running the native NVMe-over-TCP driver. So there's no fungible accelerator inside these systems. There's no acceleration from the card that we provide inside the hosts. What we will be testing is, or what we'll show is, 3 types of volumes: a raw volume, a durable volume with RF2, a durable volume with erasure coding 4+2, as well as basically integrations with our REST API, how we create volumes and detach volumes. So we'll essentially create 3 volumes, attach them to all 12 servers. We'll use FIO to do our read and write. And then at the end, we usually just kind of detach those volumes using the REST API, delete them, and reprovision them. So it's rinse, repeat in terms of what we'll be showing on the screen. Like I said, I have accelerated some of the functions in this demo because I want to show the functionality, but also I just don't want to sit here and waste a lot of time watching things happen. So as I show you here, essentially what we have is a 3-node cluster. Each one of those has 24 drives, and we have the DPUs that are sitting inside each one of those. This kind of gives you the storage system view of what we're doing. We'll also kind of show you kind of like from the UI perspective, the bird's eye view. So essentially, we're going to give you kind of that single pane of glass, that dashboard that shows you all the storage functions and whatnot. And on the left-hand side, what we'll have here is kind of like the UI or the command line that we're running through and kind of showing some of these demos. So the first one we're going to do, the first performance test I'm going to do is essentially a raw volume. So this is the API running in the background. It's provisioning those 36 volumes to those hosts, and it's kind of doing all of that in the background. And after it's done and accomplished those things, we're going to go ahead and flip over to the UI view and show the performance as it starts to ramp up. So this is essentially going to be 60 seconds of write and then 60 seconds of read at 4K. And so we'll start to see the performance increase in the system as it goes forward. And what you'll notice here too, and on the right-hand side, is the DPU utilization. We kind of capture and show that back so that you kind of understand how hard the DPU is working. So as I'm getting up to here about 18.3 million or 18.9 million IOPS across those 36 volumes, the DPU is only doing about 17% utilization across the board. And we see latencies that are pretty good here as we've switched to write, still under sub 200 microsecond latency, 18.3 million, 19 million IOPS. It's, performance when you start to speed up a video kind of fluctuates all over the place. And I have a screen at the end that kind of outputs what we've done here. But, for a raw volume where a customer doesn't need durability, they just want raw performance. They just want the ability to, provide, say, transient data or, data that doesn't need to require a lot of resilience. That's what the raw volume is really about. And the nice thing about our platform is you can kind of create individual volumes and give them each their own set of data services. So that test is essentially kind of finishing up right now. And what we'll show you here is that basically those volumes are going to be detached from those hosts using the REST API, and we'll blow all those out. I've accelerated this significantly. It takes about 2 minutes to do it. And then what we'll do is we'll go ahead and run the second test. So now we're going to leverage an erasure coded volume without any data services. So it's simply just durability to provide that erasure coded experience where essentially you can lose 2 drives in that situation, or 2 nodes in that situation because we are a node-based architecture. As I kind of move down, what I'll show is like, this is a durable volume. We have a space allocation policy that's balanced. There's no compression. There's no encryption. Our block size is 4K in this particular instance. And then I can actually kind of go get down a little bit further in the concept of, if you want to understand where data is placed, which drive it's placed on, if you want to leverage things like fault domains across the board, essentially we can kind of dig down and show you which DPU is actually allocated to which drive within inside which each node, right? So this is helpful for understanding data placement. I think there were some questions on Twitter at trying to understand where things sit in terms of how data is placed on the platform. And in a raw volume, we would simply just have the single DPU attached to a single drive. In a durable volume, traditional RF2, you would have essentially 2 drives and 2 DPUs driving that. But as our architecture kind of expands out, we want to leverage and utilize the benefit of providing this. At the same time, at this volume view, what we're showing you is you can show which host is connected to it, et cetera. And then we're going to flip over now to the actual performance test. So this is going to be running an erasure coded volume at 4+2, running that same read and write process. Now, I do see that the DPU utilization's gone up. If we think about erasure coding, it's a pretty processor intensive operation. So getting 4.5, 5 million IOPS from a write perspective with erasure coding and good throughput with really pretty decent latency. I mean, it's 110 microsecond latency at this point. That's a testament to the power of the DPU and why we focus so much on data-centric operations, which are very difficult to do. Because if I had to do this with a traditional processor, I would probably peg that processor. That's why we probably don't see as many scale-out erasure-coded platforms, because they are very CPU intensive. And that's the whole point and design behind the fungible data processing unit, is that we can do these operations much more efficiently and much more effective. So as we flip from writes to reads, we're coming in at about 17 million IOPS at the peak. And so I think it's important to call that out, that, obviously performance is a big thing, but performance at scale and then being able to align it is better. So now we're going to do that same test, except this time we're going to turn on data services. So we will turn on encryption and compression at the same time. So we just saw that first test run through. And what I want to illustrate here is that ultimately, even when we turn on the full complement of data services, we're going to be doing, I believe, encryption as well as I think it's compression at 2x. As I scroll down into here and kind of show you, expand that out. So a durable volume, it's got encryption turned on. We're doing compression at 2. And then we'll show the performance, right, is that it's almost identical. And so, like I said, the DPU utilization may go up a little bit, but we have a lot of power within inside that DPU to do these functions. And so, it's important to illustrate that, when we run performance tests and when we see a lot of other storage platforms that exist out there, usually the more data services you turn on, the slower the system gets, or there's a significant performance impact. It's not the same with us, right? The fact that we've designed a process, a new breed of microprocessor that's kind of dedicated to data-centric operations and how complex they are, and we could be that much more efficient as we do these data-centric operations. And this is just applies to storage, but it actually expands to much more within, say, the data centers all as we start to kind of go down the path of composable infrastructure. But honestly, this is the highest I've ever seen the DPU actually utilized. Interestingly enough, it probably takes about 12 standard servers in order to kind of saturate the performance of a single fungible storage node. In this case, we have 3 nodes and 12 servers. And so, we still can't really kind of fully hit the highest levels of performance that we've done inside the labs. But as this test starts to end here, we're seeing, like I said, very good read performance, very good write performance. Interesting stuff. This is the durable volume before and after. And I'll show you this here in a second as we kind of go into a regular RF2 volume, which is essentially going to be a mirrored volume as we break out what the data layout looks like here. and attaches to the different DPUs and different drives within the system. And this is not a compressed volume, and there's no encryption turned on this one. And it's simply to illustrate, I guess, the performance of durable volumes, which are basically protected. I have 2 copies of that data in the system versus a raw volume where there's no data resiliency, or an erasure coded volume where there's a higher level of resiliency. Interestingly, I look at it from the standpoint of being able to set per volume data services at a granular level means I can match applications to their specific requirements. I can say, how much capacity do I need? What kind of performance do I need? Because we also have quality of service on our system where we can set a min and max. And then what kind of level of durability or data services. So not every volume needs encryption. Not every volume needs compression. Some do. And so therefore you can kind of fine tailor the data specific aspects that the application needs to the individual volumes. The same applies for security. So we can do encryption keys at the individual volume level and then create multi-tenant space environments that customers can leverage. So as that test kind of ends here, what we're showing essentially is I can dig down as well into the individual volumes and look at their performance. We usually show like all of the volumes as they're running, but you also dig down into each individual one. So if you wanted to troubleshoot something from a performance standpoint or look at it a little bit deeper, you can kind of go at a little more granular level. So as we see, as this test kind of ends up, I think we hit about 18.2 million IOPS in that particular test. As we flip from reads to writes, we're going to detach all these volumes. And the next test we're doing is essentially illustrating the power of the API. In container-based environments, providing and provisioning a lot of volumes at a high rate of speed is really important. What I'm doing here is I'm basically creating 1,000 volumes in under 2 minutes. And I've sped this up considerably because, so I don't want to like watch all this run forever, but, in the interest of time, being able to do high transactional volume provisioning, and then after the flip side of this is I have 1,000 volumes, I'm going to turn around and I'm going to delete all of them. The whole process, like I said, create 1,000 in 2 minutes, delete 1,000 in 2 minutes. If I look at the kind of industries and customers we're going after, where we're trying to look at a lot of bare metal composed infrastructure with containers, or say OpenStack or other infrastructure, or bare metal completely, being able to have a highly performant and scalable API construct that can really kind of do a lot of work in a rapid amount of time is really beneficial. It's another benefit of separating control plane from the data plane, whereas I can leverage the full power of the CPU and the control plane to do its specific operations, and I'm not sharing with the actual storage platform itself. So just from a performance construct, what we had here is essentially raw volumes. We hit about 18 million, 12.5 write. A standard durable volume where it was just erasure coded 13.7, 4.7. A durable volume erasure coded with compression and encryption. So the one thing I want to point out is the delta between turning on those data services from a write standpoint is almost negligible. It's only 100K IOPS, and just under a million within the between for the reads. And then also we saw really good performance with a durable volume as well, and creating those volumes. It's like I said, the DPU was designed to facilitate and support data services and do them very, very well. I don't think I could do this with a traditional x86 processor and still get the same level of performance. So that's kind of the performance demo that we've done. Now I want to show you the Fungible Storage Initiator. It's pretty much a similar set of type of tests. We're not going to do as many of them, but essentially we're going to create a volume on an FS1600, which is our fungible storage node. We will show you the volumes as they attach to the FC200, which is the Fungible Accelerator card. It looks a little more something like this. It's a little simpler implementation. We just have a single FS1600, a single node for server, but the same kind of networking construct and 601 gig links that we connect up to. So what we're doing here is essentially, once we put a Fungible Accelerator card inside the system, it just shows up as a PCI Express device. In this case, we're providing that offload for NVMe-over-TCP. I've provisioned 10 volumes to this particular card. They would just show up inside the system as it's a raw device or a raw disk. And then what I'll do is run a quick test. Now, what I want to show is the capabilities of the Fungible Accelerator card, essentially doing reads and writes just as we did before. roughly about 2.6 million IOPS from the host. And the interesting thing, I mean, it's a lot to drive 2.5 million IOPS or 2+ million IOPS from a server individually. The accelerator card, like I said, offloads those functions and really accelerates those processes. So while we can do around 2.6 million on the host from a read, and we're going to do the same read and write test, and then it looks like we're doing reads right now, and we're coming in at about 2.1. Point of construct is that the whole goal here is to offload those cores. So what I've seen in many tests and what we see here is essentially I can significantly offload CPU resources from the server. And the goal there is to free those resources up and give them back to the host to run applications, to run virtual machines. And we kind of talked about the concept of Nitro and AWS, and this is more like Nitro for the masses as we're able to kind of provision and offload these complex data-centric tasks to drive a high amount of I/O. Because if I had to do this using just a traditional x86 processor, usually what happens is I start to saturate. You get to 1 million or 2 million IOPS on an individual server, you're saturating most of the CPU in there. Some of the tests that we've done, I've seen customers drop as much as 75% CPU utilization at very high speeds and high performance. And the difference too here is that I can usually drive about 50% more I/O leveraging the Fungible Accelerator card as an initiator inside the hosts. So output from that test, essentially, we reduce the CPU host utilization, which frees up resources or allows customers to leverage lots of different types of CPUs, maybe even fewer cores, because we're not consuming all of those resources to do the high performance I/O operations. We saw about 2.2 million IOPS from a read standpoint, 2.6 from a write standpoint with the storage initiator card as we've put it inside the hosts. So the last piece that we're going to jump into is obviously we see a lot of customers that are very interested in leveraging bare metal container workloads as we see that we can kind of significantly reduce the overhead of having to introduce a virtualization layer in there and go straight into bare metal. So I have a simple 3-node Kubernetes cluster. What I'll do is basically kind of run through the same type of classes. We're going to create a pod with storage classes, and then we're going to go through and kind of show and illustrate how we integrate in there. So our platform essentially, we have a CSI driver. I'm going to create this container application with the storage attached and kind of illustrate some of the details around how we integrate in there. So what we're essentially doing is providing that NVMe disk into the actual container-based application. As I start to kind of move forward, what I'll see is that our CSI plugin is a sidecar that sits inside the Kubernetes platform. We basically have all of our different CSI integrations to pass credentials and provide API access from the container. And then we can go in there, look at the YAML file and set the configuration parameters for each of those individual functions. So in this case, I have a raw volume that I'm providing. It's 8 GB in size. And it's all about how do we get towards that that programmable infrastructure, and then this application is simply just going to run the FIO test and drive a little bit of IO so that we can kind of create like a real-time application. So in conjunction with having a very elegant and intent-based API platform, being able to do a significant number of IO operations, but also API operations that scale is paramount to how we want to integrate within the container-based ecosystem. So kind of output there is that essentially we have the ability to provide all of the same levels of durability at the per volume level to each individual container. And we can also integrate things like snapshots and clones and per volume based quality of service for persistent volumes in block mode, or even for non-persistent solutions that sit, or volumes that sit and exist out there.